Hello?
Yes.
Okay. Because for the Friday's course, I have another course from the 8 to 10. So it's a little late for this course. Can you find this PPT? Okay. We have introduced the resistive nonlinear circuit. We have introduced the nonlinear resistor circuit. The Kessel-Keller function is still linear. The Wieser function is nonlinear, and we have discussed if the circuit contains only one nonlinear resistor, we can treat the linear part as Thevenin circuit. And we have also discussed the drive point figure. For the transfer figure, we don't care about it. For the small signal method, the small signal method always used in the communication circuit or the transistor circuit. Transistor circuit always in the small signal method. It's an AC signal plus a DC signal, AC plus DC. And the AC is always much less than the DC. For example, maybe it's 5 watts, but this is 1 milliwatts. For this kind of signal, we use the small signal method. We can use the Taylor series to make the question simple. A DC source, a AC source. The AC source is much smaller. At any time, the US, the DC, this DC, sorry, this DC, this AC. The DC is much larger than AC. The RS means a linear resistor. This means a nonlinear resistor. I equal to GU. This is for the description of the nonlinear resistor. For the Keller function, US plus UST, these two sources will be this voltage U and this resistor voltage RSI. Step 1, we assume there's only one source working alone, only one source. Only the DC work, The AC not work. The AC is here. We assume the AC is 0, Then we can find the UIT and IIT, UT and IT at first. This straight line means this part, the Thevenin part, calculate. This red line means the nonlinear part. The cross point is the solution. I equal to GU, US equal to RS plus RSI plus U. This means the total function, So it will be US equal to RS multiple GU plus U. So from the function, we can solve the voltage U and then find the current I. For this work point, we use I0, U0 to express U0, I0. We call it as a state work point. It works only under the US, the DC source, no AC source. The step 2. The DC, AC work together. So the UTIT, pay attention, the UTIT. This is DC, this is AC. This is a linear resistor. This is nonlinear. The UTIT means this position. UT. This IT. UTIT. So it will be because the AC worked. The U0, I0 means no AC, only DC work. Now the AC worked, so they will make small changes. delta U, delta I. This function is the VooV function of the nonlinear circuit. From the Taylor series, I equal to GU, so the I plus delta I equal to GU plus delta U, and the Taylor series, they should plus dg du second order delta U square and 1/2 and plus higher order We ignore the higher order part. Only concern about the first order. This is the first order. So this is dg du, the differential. I0 equal to G0, U0. This is the static work point. So this part delete. Delta IT equal to this part. dg du U0 delta G ut. And this part, we define it as a dynamic admittance. This dynamic admittance. So for this is the AC source caused result. So the AC caused delta I and AC caused delta U seems like very similar to linear. They should be nonlinear, but we ignore the high order, then they will be linear. So the delta U, the delta I equal to delta U multiple dynamic admittance. Just dynamic admittance. Because US equal to I0 and U0. So UST, the AC source equal to RS delta IT. This is a linear part, linear resistance. Delta UT, the delta UT is 1/GD delta IT. So this is for the nonlinear part. This is the AC source, the RS. For the nonlinear part, now we use this is linear resist, this is nonlinear resist. But in the AC circuit, we use a 1/GD or RD dynamic resist to express it. So we change the nonlinear circuit to linear circuit, based on the promise is the AC source is very small. That means the delta I and the delta U is very small. Because it's very small, so they will be similar to a linear component. Or we can fit this problem in the code. This code means for the VooV function of the nonlinear resistance, because delta U delta I is very small. That means it change the static work point. It only change from this part to this part, very small part. So for this smaller part, the delta U, this delta I, we can treat it as a straight line. This is from the figure meaning. So we treat the delta U delta I as a linear part, although it's nonlinear, totally nonlinear. But in this small part, we can treat it as linear. So small voltage and current caused by small source. So we go to the small signal equal circuit, AC source work alone. So this is a linear resist to express. Use it to express. So step 3, add the total voltage and the current. This is a DC result. This is AC result. The total result. we have introduced the small signal method. Now we introduce the segment linear method. We cut the nonlinear curve to several linear. Cut the nonlinear curve. Nonlinear curve to several linear segment. Linear segment. Use linear line to approximate every segment. For example, this is a nonlinear circle, but we can treat every part as a linear part. Treat this part as a straight line to express this part as straight line, and this part as a straight line, this part as straight line, and this part as straight line. So use linear straight line to approximate every segment. So we call this segment linear method. Use several segments to express every part resistive UI relation. Express the nonlinear circle to several linear circles, and find the solution of every linear circle. For this circle, this total nonlinear curve, we treat as 1, 2, 3, 5, 4. 1, 2, 3, 4, 5. Total 5 linear resistors. And then find the solution of every linear part. But should check the every solution. Check if it is reliable. For example, for this circle, this is nonlinear. But we can use two straight lines to express. When the I descends IA, this IA, the segment OA, we can use the resistance RA to express. It is equal to tan alpha. When the I larger than IA, we use this straight line to express. The RB is tan B. So find the equal circle. For the OA part, we can use the resist to express. For the AB part, we should use a Thevenin circle to express. There will be a voltage source, and the serial connected with the resistor. For example, for this resist, nonlinear resist, we know this is the work. This 0. This is none of the nonlinear part. For the nonlinear part, the change point is 2. Is 2 volts, 1 ampere. So from 0 to 2 volts, it is 9. From 2 to 4, it is 9. Now we try to find the solution of this circuit. For the any segment, we can use the Thevenin circuit to express. For this part, segment 1, I less than 1 ampere, U equal to 2I. So for this part, we can treat it as a 2 ohm resist, and the US is 0. U 0. For 2 to 4 or 1 to 3 part, I larger than 1 ampere, the U equal to I plus 1. So the R is 1 ohm, US is 1 volt. So for this function, we can use 1 ohm, serial connect 1 ampere to express. This total U, this total I. So this U means this voltage, this I means this current. U equal to I plus 1. 4 equal to 3 plus 1. For the segment 1, this circuit, we assume it works in the segment 1. So that means when the current less than 1 ampere, it's 1 ampere, it's this circuit. And then we found the solution. We found the solution is 1.75 ampere. It's larger than 1 ampere. So this solution is wrong because we assume it's less than 1 ampere, but the solution is larger than 1 ampere. So this is not the real solution. So this model is wrong. And we use the model 2, assume the I larger than 1 ampere, use this circuit, and find the solution 2 ampere. So assume it's larger than 1 ampere, and the solution is 2 ampere, so it's right. This model is right. So we ignore the first solution. Ignore first solution. So only this solution is right. Sometimes there will be only one solution, but sometimes maybe there will be several solutions. For example, for this circuit, and this 17 part, they will have 3 solutions. So every solution is right. But for this circuit, the first solution is wrong. Okay, my conclusion. We have introduced to the small single method. Small single method. It only uses for the circuit have 2 sources, the AC source and the DC source. It's an DC source. And the AC is much less than DC. And we make AC work alone, make DC work alone, and then AC work alone. Then found an equal linear circuit. And then we introduce the segment method. Segment linear method. For this 2 kind of method, the segment means we treat a nonlinear curve. We use several linear segments to express. To approximate it. So these 2 methods are all use approximate linear to solve nonlinear circuit. So this is the essence of these 2 methods. For the diode circuit, this is a special circuit. We will introduce a promised state method. For example, in this circuit, there are 2 diodes, diode 1, diode 2. Now we try to draw the UI relation. So we try to find, maybe this is U, and this is I. We try to find a tree. Maybe it will be like this. Maybe. We try to draw the line. Because the diode is nonlinear. This is nonlinear. For this kind of circuit, we use promised state method. What does this mean? We can assume the 2 diodes are all open. Diode 1 open, diode 2 open. And then we assume the diode 1 short, diode 2 open. And then diode 1 open, diode 2 short. And all these diodes short. So for the 2 diodes, there will be 4 kinds. For the 3 diodes, there will be 8 different circuits. 8 circuits. For the circuit, at first we assume these 2 open. Assume these 2 are open. Because diode 1 open, diode 2 open, so this will be 0. I1 0, I2 0. So the I3 will equal to I. This means this current flow in this road, in this path. So the total U, this is U, equal to 1 ampere multiple I. minus 2 multiply I3. I3 is I. And then plus 4. So it will equal to U equal to 1 multiply I plus minus 2 multiply I3. I3 is I and plus 4. So it will equal to minus I plus 4 or I equal to 4 minus U. So if the diode 1 and diode 2 are open, then I equal to 4 minus U. When we try to make these two diodes open, we should make sure the U1 is here, plus negative, positive, negative. The U1 less than 0, and the U2 less than 0 also. The U2, that means U1 less than 0, and U2 should less than 0. The U1 is here. It will be minus U. U minus this U voltage, minus this voltage, and minus this voltage. So U minus I minus 2 less than 0. And for this voltage, this voltage will be minus 4. We found out this voltage because I equal to 4 minus U. I is 4 minus U. So it will be 4 minus 4 plus U minus 2 less than 0. So that means the U less than 3. U less than 3. This is for the D1. If the U less than 3, then this U1 will less than 0. So it will be open. Now we try to find the U2. The U2 is this voltage. U2 equal to I minus U. U2 is here. So U2, this U, this I. U minus I multiple 1 will be this voltage. This voltage is a minus U2. So the minus I minus U will be this U2. And this U2 should less than 0. Then the UD2 will open. This part is 4 minus 2U. I is 4 minus U, so 4 minus 2U. It should less than 0. That means the U should larger than 2. So for the U less than 3 and larger than 2, then D1, D2 will really open. And in this part, the I equal to 4 minus U. And then we assume the D1 short, D2 open. D1 short, D2 open. The D1 short. That means there's current here. The D2 open, there's no current. So the U will be equal to I plus 2. The U, because this is a short. These 2 volts. These 2 volts and this resistor voltage will be this voltage. U voltage. So the U equal to I plus 2. And 2 equal to minus 2 I3. That's for this part, for this sector. Because this is 0, so this is 2. Minus 2 I3 is this voltage, plus 4. So we can find that I3 is 1 ampere. So I3 will be 1 ampere. So if D1 short, I3 will be 1 ampere. The U equal to I plus 2. Now we judge the D1. If we try to make D1 short, So the I1 should larger than 0. I1 should larger than 0. The I1 is I here, just I minus I3, just I3. And I3 is 1 ampere. And the I is U minus 2. I is U minus 2. So this means the U should larger than 3. Larger than 3. So if the U larger than 3, this will be short. This will be short. So if this is short, that means from this point to this point is 2 watts. If 2 watts means the U2 is minus 2, U2 minus 2. So the D1, so the D2 will open. It will open automatically. It will be open. So if this is short, it will open automatically. So this means if the watt larger than 3, the D1 will open, will short, D2 will open. And the solution is I equal to U minus 2. And then we assume the D1 open, D2 short. This open, this short, this short. So the U1 is the I1 is 0, open. U2 is 0, U2 0. So the U will equal to I because this short. So the U will equal to 1 ampere, 1 ohm multiple the I, multiple I. The UI relation, this is UI relation. And this is short, So we can find the I3 easy. It will be minus 2 ampere. This will be 2 ampere. Will be 2 ampere. And because this is short, because this is short, so this will be 0 watts. So this U1 will be minus 0. So the U1 will open automatically, open. But if we try to make this part short, if we try to make it short, then the problem is the I2 should larger than 0. I2 plus I is I3. This is I. This is I2. This is I3. I3 is 2 ampere. So the I2 plus I is U. That means the 2 minus U should larger than 0. So the U should less than 2. So if the watt less than 2 watts, the D2 will short. D1 will open. And then the solution is I equal to U. And then we assume the D1, D2 are all short. U1 short, D1 这个D1 short, it will be 0. D2 short will be 0. If U1 short, so this point is 0. So from this point to this point, it should be 2 watts. Then the U2 should be minus 2. This means it's conflict. So that means if U1 short, D1 short, the D2 kind of short. So this is not a solution. So only these three cases. So from these three cases, we can draw the Q. When the U less than 2, sorry, this is 2, this is 1, this is 2, this is 3, this is 4. When the less than 2, I equal to U. From 2 to 3 is 4 minus U. When the U larger than 3, it's U minus 2. So we draw the gyro point figure of this nonlinear circuit. This method we call it as the promise state method. Promise state method. We assume the circuit, the diode. If the 2 diode, assume the 4 keys. If the 3 diode, there will be 8 keys. Then we assume the 4 keys at first, and then found every case UI solution. Then from the UI solution, we found the case condition. We assume it's open. Then we judge if it will be open. If it try to open, we can find the solution. Just find the solution. So this is a promise state method for the circuit contain nonlinear diode. The steps: assume diode state open or short. Then according the state, get the UI relation. And according the open diode voltage expression and short diode current expression. If short, the current I should larger than 0. If open, the voltage should less than 0. We don't care about this. Now introduce the nonlinear dynamic circuit. For nonlinear dynamic circuit, it contains nonlinear circuit contains a capacitor or inductor. If the only one dynamic component, we call as the first order nonlinear circuit. If 2 LC component, we call as the second order. The LC can be linear or nonlinear. So the function is a construction constraint and the plus component constraint. The construction constraint means KCL. The uniform function will be like this. The first order. This is a variable, maybe the u or I, and it will also contain time t. The second order will be second order differential. Self-control circuit. This is a concept, a new concept. If the circuit contains DC source, and the time invariant component, we call as self-control circuit. If self-control circuit, the source is DC, all other component is time invariant. So the function will don't contain the time t. It will be like this. For example, the RC DOC dt plus UC equal to 5 watts. So in this function, only the differential contain time t. All other positions don't contain time t. So it will be like this. Don't contain time t. No time t. So the first order and the second order will be like this. Don't contain time t. We call this self-control circuit. Self-control means the circuit change with time, not change with the source time. If the circuit is a AC source, for example, just AC for the source, so the circuit will be RC, the RC DOC dt plus UC will equal to sin omega t. So this function will contain t here. So it's not self-control. We don't care about this question. We just care about the DC source. We care about the self-control. For any nonlinear circuit solution, now Huminghou found 4 kinds of solution. The first kind is balance point, and then periodic solution, or quasi-periodic, and the chaos solution. The total four. For the balance point, periodic solution is easy to understand. For this two, it will be a little difficult. Let's have a rest for 10 minutes. Then I will introduce this later. Break for 10 minutes, everybody.